So I know this is an online lecture, but I would like this to be as close as possible as a real lecture, like in-person lecture. So I ask people, yes, if you have questions, please stop me, right, when you have the question. I know that some people are in places that are, the internet's not that good, or they're in a busy room or something like that. So if they prefer to use the chat, that's okay. But
Yeah.
if possible, to keep this as close as in-person lecture as possible, I would invite everybody to, start the camera, open the mic, and ask the question as if it were like a regular lecture.
Okay. So I think it's already 11, so you can start then, please.
Okay, let me share my screen. So can you all hear me and see my slides?
I see it.
Good,
Yes, we can see it.
great. Okay, so first of all, thank you, Gaston, Tobias, Andrew, Raul, for this invitation. I'm very happy to be part of this school. As I was telling Gaston, I don't know if everybody had joined at that point. I prefer, in-person lectures. So let's try and make this online lecture as close as possible to a situation that everybody was in the same room. And what do I mean by that? If you have a question, if you can, please open your microphone, your camera, and ask your question. Otherwise, I'm keeping the chat open, so if you want to type your question, that's also fine, okay? Sometimes it takes a while to type the question, so just drop me a line saying I have a question, then I can stop the lecture, and so you have time to write the question, and I'm not, 3 slides after your question. And well, that's it. So for those that don't know me, I'm Lucas Madeira. I'm a postdoc here in Brazil, University of São Paulo at São Carlos. And I'm going to give this intro lecture on low energy scattering. And let's see. It's not changing the slides. Okay. And for those that are outside Brazil, so next week you'll be kind of here if my geography is not that bad. That's São Paulo city. I'm here in São Carlos at the Institute of Physics, São Carlos Institute of Physics, and I'm working in an atomic physics group. I do theory, but the group here produces Bose-Einstein condensates. Joseph has a question. Will the slides be provided? Okay, so what I did, Joseph, thank you for the question, is if you go to the website, you'll find that next to my name here, you have this link here that forwards to a paper that I wrote with a master's student, my master's student's Matias. And it's pretty much the content of these lectures. So if you want to follow my lectures reading alongside this paper, that's fine. Otherwise, I think I can send also these slides, but what I can do is at the end of a lecture, I send the slides up to the point that I got so that you guys can have something to read. Is that okay, Joseph?
Yeah, thank you. I think having the slides would be very nice.
Great. Okay. Yes, I'll send them to you.
Yeah,
I cannot promise that I'll send in advance, but I'll send later.
you can send it there so we can post it on the site of the school too.
Perfect. Okay. As I was saying, the group that I work here, they do Bose-Einstein condensates. They have these huge experiments that you can see here on the right, very complicated ones. And then you can ask yourselves the question, okay, this is a school on how to get nuclear physics from QCD. Why is that somebody from an atomic physics background is going to give the first lecture? Well, the answer is because this low energy scattering process, they are universal. They pop up in several areas in physics. So what I'm going to teach you today works well for atomic physics. It's going to work in nuclear physics, and it's going to work in particle physics, as long as we are talking about low energies involved. Okay. I just showed you, I based this short-term course on this paper that I have with Matias. For people in Brazil, it's this Revista Brasileira de Ensino de Física. For people abroad, it would be the Brazilian version of, I don't know, American Journal of Physics, something like that. So we try to be as pedagogical as possible concerning this topic. So if you like, you can read it. And if you have some feedback, please let me know. If you glance at this paper and you say, Lucas, I don't like this, I prefer textbook, that's also fine. So you can pick your favorite quantum mechanics textbook. It can be Griffith, Sakurai, Merzbacher, Shankar, your pick, okay? All right, so the title of my course is An Introduction to Low Energy Scattering Quantum Mechanics. So as a student, every time that somebody said introduction in their title, I was afraid that I was going to get something like those Springer books that are around, that they have the title of the book is Introduction to That Thing, and the subtitle is really for only the people that already know the topic. I don't know if you also have this feeling when you pick one of those books. I'm going to try as hard as possible not to do this, okay? So if you never heard of scattering, I hope you can follow my course. But if you already have some background on scattering, I hope it's a refresher. And if at some points in my lectures you say, Lucas, I don't know what's going on, please stop and help me, get my bearings. Please let me know, and I'll do the best that I can to have everybody following what I'm talking about. Okay. So for this crowd, I don't think I have to say a lot about why we should look at scattering, but I have this motivation slide anyway. From the experimental point of view, scattering is what we do when we study physics, right? So we look at collisions and stuff like that to see what's going on. And I invite you to think about your research, about what you saw in textbooks, what you see in this course, and think about, every example that you're studying a system that's really looking at these collisions, this scattering process. I'm going to start the course on general scattering, but very quickly I'll focus on low energy scattering. That will be the main topic of discussion here. I saw that you're going to have next week a course on relativistic scattering. So you'll have this, both courses, they're going to cover scattering in general. So I have one question for you, which is kind of a provocative question, but to get you thinking about this. So I keep saying low energy scattering, low energy scattering. What's low energy? So can anyone tell me what's low energy? How much is that?
Small compared to the pion mass.
So somebody said small compared to the pion mass. So any more guesses? It's going to be this awkward silence until somebody participates. In my lectures, I like people participating. Pablo says non-relativistic. Okay, but lots of stuff are non-relativistic. Condensed matter is non-relativistic. I don't know, Bose-Einstein condensates, they are. Nuclear structure is low energy. everything that I heard up to now, it's correct, but I want to provoke you guys. Come on. Cauê says, energy low enough so that we can't employ perturbative QCD. So what I'm getting from everybody that participated are examples that you can apply this low energy scattering. But really, the answer to this question is it depends. Because, you know, in physics, low and high, it's relative, right? So when I say low energy, you should ask what kind of system you're talking about, Lucas. The pion mass, the first answer that I got, like 200 MeV, when you're doing atomic physics, that's a lot, because in atomic physics, we are talking about electron volts or milli electron volts, so 10 to the -3 electron volts. So you should always, when you're thinking about low energy, high energy, first ask what kind of systems we're considering and the typical scales of the system, especially the energy scales. And low is going to be if it's much, much smaller than all quantities involved. So really this depends on the problem you're talking about. Okay, so I like that several people participated. I hope more people are not so shy and participate in the next few questions that I ask. Okay. So what's scattering? Like very generally is when you have some object interacting with something that I'm going to call a scattering center. In the classical view, probably you worked this problem in undergraduate classical mechanics. You have some particle that's approaching a scattering center here that replaces the origin. And if it's repulsive, it's going to be scattered by this scattering center. And then you can talk about the trajectory of this particle when it was scattered. You can talk about particles. You can also talk about waves, like electromagnetic waves. And here, what we are interested in discussing is a quantum particle. So we are going to look at this classical version of this classical view here and ask ourselves what happens if instead of a classical particle, we have a quantum particle. Okay. And for that, we're going to talk about quantum scattering theory. And this is going to be the picture that I want you guys to have in mind when we're discussing this problem. So instead of a particle, I'm going to have a plane wave. I oriented my axis along z. So we have some particle that starts very far away from my scattering center that's here. And then this plane wave is going to interact with this scattering center, giving rise to a spherical wave. So a wave that's concentric here with this scattering center, okay? So the particle starts very far away, and then it's scattered by this thing that's near the origin here, okay? So far, so good? Yes, no?
For me, it's okay.
Okay, when I ask this type of questions, you can always say, Lucas, go slower, faster, okay? Okay, so being a little bit more mathematical about it, okay? So what we're going to do in this course, we're going to talk about elastic scattering. We're not going to discuss inelastic. We are going to consider that we started our problem with a plane wave that's at some point is going to reach the origin where our scattering center is. And this is the third one is a very important hypothesis, is that the thing responsible for scattering, so the scattering center, is going to be local and finite ranged, okay? So in this last figure that I showed, the scattering center, the potential, for example, it acts in a finite region around the origin. So here we have some V that's not zero. But outside of this region here, we're going to have a free particle, okay? So that's very important in the stuff that we're going to derive in the fall, okay? So we can write, or better translate last picture into a wave function that has one component that's related to the plane wave that hits the scattering center, the spherical wave that's produced when that happens, and some coefficient here. This function here is going to tell us how much or how strong was the scattering, because this is the thing multiplying that spherical wave of that first picture. I'm just going to motivate this qualitatively in these slides here in this beginning of the course. If we have time at the end of the course, I'm going to derive this formally, okay? So if we have time, I can go a little bit more on deriving this like with formal scattering theory. If not, please have in mind this picture that I showed in the last slide, okay? So what's really scattering from the quantum mechanical point of view? You start with some initial state, and then after scattering has occurred, you end up with a final state. So what's the hard part is getting the operator or what happens to start with some initial states and get to this final state, okay? Since I told you that the particle starts far from the scattering center and in a region that has no potential, it's a free particle, we can assume that the initial state is a plane wave with some energy and some momentum, k. And it's going to be an eigenstate of this Hamiltonian H naught. That's just the kinetic energy because there is no potential. And then what's scattering? Scattering is going to be a potential term that acts, that's turned on when the particle is near the origin, okay? Any questions?
No.
Okay. I think everybody's familiar with doing the real space representation of plane waves. Okay, so I'm just writing this here to be thorough. I should mention that I'm going to write those L to the 3/2 here for the plane waves. But since we're talking about scattering and we want this continuum character at the end of our calculations, so at some point I'm going to take those typical length scales to infinity, okay? But that's just a side note. This will happen naturally when I'm doing working out the math, okay? So some more hypotheses, because this is a hard problem. So I'm going to focus on some specific cases that are, well, they're specific, but they're going to be helpful in many settings, in many problems, in many systems. I'm going to orient that plane wave just as I did in that very first picture along Z without loss of generality. And I'm going to do something that's going to help the calculations a lot, which is to assume that that scattering center at the origin has a spherical symmetry. So in the last slides, I was writing the potential as a function of the position vector. Here, I'm going to write the potential as a function of just the distance from the origin, okay? If I do that, that term that was multiplying that spherical wave in the previous slides, since it's spherical symmetric potential, it's not a function of our vector anymore, it's just a function of theta, okay? So if I have this spherical symmetry, what this is telling us, this invites us to solve the Schrödinger equation in these spherical coordinates, okay? And the equation is going to have the potential only for distances around the the origin. As I said, my potential is going to have some range that I'm going to call capital R here, and it's going to act only in this region here. And outside of this, this region here, the potential is going to be 0, okay? And then I have a free particle. So the first thing I'm going to do is solve the Schrodinger equation for those two cases using spherical coordinates, okay? So it's something that I hope everybody has seen, at least in an undergraduate quantum mechanics course. For example, when you were solving the hydrogen atom or something like that, okay? So I'm going to do what's called a partial waves expansion. So I write down that Laplacian that I had in the last slides as this thing here in spherical coordinates, usual spherical coordinates. And I'm writing this Laplacian as a physicist, not as a mathematician, because I'm already introducing the angular momentum operator, or rather the square of the angular momentum operator, okay? And so it's the usual operator that you guys, I hope, are familiar with. It's a z component, Lz is given by this phi derivative here. And our wave function that's going to depend on r, theta, and phi. It's going to be, I can construct a complete set of eigenfunctions if I consider the Hamiltonian. The corresponding eigenvalue, of course, is the energy. I can use the total angular momentum and get the quantum numbers associated with the angular momentum. And its projection, I can use also Lz. So if I use those three, I have a complete set of eigenfunctions. Again, this is the same thing that you would do solving the hydrogen atom in your undergraduate physics course. Any questions?
No.
Okay. Is this new for anyone? Okay, so everybody's familiar with this. So I'm going to propose. Yes, questions? Yes.
Yes, I do actually. Can you go back to the previous slide?
Sure.
Why is it important that the set is complete?
So we're
set.
going to, yes. So we are working in 3 dimensions. I should have mentioned that. So we're going to consider scattering in 3 dimensions. In the following, I'm going to use a lot the quantum numbers related to this problem. So if you want a 3-dimensional, if you have a 3-dimensional problem and you want to index your wave function with those quantum numbers, I need 3 quantum numbers. And for that, I need to pick 3 operators, and they have to commute, and they have to form a complete set so I can describe my wave function in this matter. So I hope that in the next few slides, it's apparent why I chose these operators rather than other possible choices. And if it's not, I'm going to ask you to stop me again and say, okay, Lucas, it's not clear to me why you chose those 3. Is that okay?
Okay, thank you.
All right. Okay, so I'm going to propose a separate solution, so a product solution. And for that, I'm going to assume that you worked out this problem for the hydrogen atom or any problem with spherical symmetry at least once before in your life, because I'm going to already use the fact that for any spherically symmetric potential, the angular component, so theta and phi, is going to be given by the spherical harmonics, okay? So this is not only true for the hydrogen atom, but also for any problem with spherical symmetry. And so all the angular part is going to be captured by the spherical harmonics that I also hope you're familiar with. So what's left is it's just the radial part of the wave function. So I didn't do this in detail in the slides, but what you have to do is you take this solution that I proposed, you substitute in the Schrödinger equation in spherical coordinates in the last slide. Then you separate everything that depends on r on one side of your equation, on theta and phi on the other, and then you get those constants of separation, and you get a differential equation for your angular part, and you also get a differential equation for your radial part, okay? For the radial part, as you can see here, you're going to have terms that have first and second derivative with respect to the coordinate r. So I'm going to do one substitution. That is, I'm going to consider this new variable u here, which is related to this other one by a factor of r. And if I do this substitution, I get rid of the first derivative. I end up with a differential equation that has only a second derivative. So usually we call this one here, this a here, radial wave function. To be formal, I would have to call this u here reduced radial wave function. And sometimes I'm going to drop the reduced word because I don't want to keep saying this huge name. But keep in mind that they're related by a factor of r, okay? Once again, this is the same type of thing that you did when you were solving the hydrogen atom, okay? So you get this differential equation here. I defined this k squared, the usual k that you are used to. This u here is related to the potential by only those factors of h bar 2m. And the separation constant, since we already know the answer of the problem, I write as L plus 1 as the separation constant, okay? So our problem now lies on solving this differential equation, okay? If I have to consider two cases, remember that my scattering center works only for distances smaller than some range r of this potential, and outside this potential is 0, okay? So I'm going to start with the first case, which is in this region where my potential is 0. So for distances larger than the range of my potential, okay? Why I'm doing that? It's because for this case, the potential is 0. I have a much easier equation to solve. It's the free particle equation in spherical coordinates. And then the solution, this differential equation has a solution related to the spherical Bessel wave functions, okay? So if you've done some kind of mathematical physics course or something like that, probably you saw some special functions. Spherical Bessel functions are usually covered on these courses. Because of this, this is the reason, because when you solve the Schrödinger equation for a free particle in spherical coordinates, you get those as solution, okay? So I go and write the solution to my equation as a combination of spherical Bessel functions times r here, okay? And if you're not so familiar with those functions, I've written down the first few of the two functions. These are called spherical functions, spherical Bessel functions of the first kind. These are of the second kind. And I've also made some plots so you can get a sense of what those functions look like. I think the things that are relevant here about them is that for the first kind, the only one that's not 0 at the origin is the 0th order spherical Bessel function. And for the second kind, what's interesting about them, it's all of them diverge at the origin. Okay. So when we do physical considerations about those functions, we should have that in mind, that the first kind is well behaved close to the origin, and the one of the second kind, it's not. Okay. So far, so good.
Yes, that's okay.
Good. Okay. If you don't want to work with those spherical Bessel functions, you can also use what are called sphero-Hankel functions, which are just combinations, linear combinations of spherical Bessel functions. And they're really much more convenient to express that spherical wave. Remember that I had some plane wave along Z that hit the scattering center. And when it hit the scattering center, it was producing these spherical waves that were something like e to exponential of IKR over R. And these are much easier to relate to those Hankel functions. Okay. It's kind of similar, the analogy of when we have a complex exponential, we decompose it as cosine and plus I sine. Here we are going to have those spherical Hankel functions being spherical Bessel functions of the first kind plus or minus I, the second kind. And you can see here the spherical functions that I'm showing here, that they are really more appropriate to work in this. They're closer to what we want in the spherical, in the scattering scenario. Okay. So I'm going to write the solution to that differential equation as a linear combination of those spherical Hankel functions. Okay. So this is all just math, but we're using math to our advantage to have to make our calculations easier as much as possible. Okay. All right. So everybody knows that when we have a free particle, we have just a plane wave. Okay. What's the thing about a plane wave? I can, in this spherical coordinates, if it's oriented along Z, I can write Z as R cosine theta. And then I have my plane wave here along Z in spherical coordinates. And angular momentum is one of the few quantities in physics that depends on your choice of coordinates. And you can look at this and pretty easily convince yourself that since it's extending through all space, a plane wave along Z contains all possible momentum, angular momentum values, contain all possible values of L. If you don't like my physical justification, you can use this mathematical equality here. It's called Rayleigh's formula. On the left-hand side, I have a plane wave along Z. And here I'm expanding it as a sum into all these angular momentum components that I'm going to call partial waves. So a partial wave, it's going to be L equals 0 is one partial wave, L equal 1 is another partial wave, and so on. That's going to be related to those spherical Bessel functions. And also the angular part is going to be given by these Legendre polynomials. Okay. Notice that I only have one type of those spherical Bessel functions. That's because, as if you remember the plots that I showed earlier, the spherical functions of the second type, they diverge at the origin. So since that's not going to be physical in our case, in this expansion, we only have one type of those. Okay. And I can always write the spherical Bessel function of the first kind as a linear combination of those Hankel functions. I realize it's a lot of math, the next few slides, we are going to have even more math. But as much as possible, I'm going to try and focus on the physics of the problem and try to translate the equations into what's happening physically. If I'm not doing a good job at that, please let me know, okay? Any questions so far? Okay, Pablo says okay. All right, so as I said, the problem is going to be a plane wave that hits the scattering center. This plane wave is coming from very far away. And since the range of this potential is finite, it's going to be only at some r close to the origin, very far away. So if I look at large distances from the origin, I can ask what happens to my wave function there where the potential is clearly zero because it's very far away from the origin, okay? Well, every special function that I showed you so far, you can look up in books for the asymptotic behavior or what happens to them when they have large arguments, and you can get the expressions for these. So we can ask ourselves what happens to this plane wave here when I'm considering large distances, when I'm very far away from the scattering center, okay? So I just substitute these two limits that I'm showing in this first part of the slide. And here I have what's the wave function of, or better, what's the plane wave, how it looks like when I'm very far away from my scattering center in terms of these exponentials here, okay? So what's interesting about this equation? Let's focus on these two terms inside these square brackets here, okay? So what's the first one? The first one is a spherical wave. It's an outgoing spherical wave, meaning that I have my origin here, and this term represents this wave going away from my spherical center. How about the second term in the brackets? It's this one here. It's an incoming spherical wave. So it would be something like I have my origin here, and it represents a particle that comes doing this towards the origin, okay? This is a little bit trickier to prepare experimentally. Experimentally, it's much easier to consider, things going away from the origin, okay? But that's the physical interpretation of these two components here of a free particle solution very far away from the origin. Can everybody see that?
Yes, I can see it, but I have a question. How do you,
Sure.
did you get to that equation exactly? I mean, how?
Okay, so I'm assuming this
Okay.
one. So I'm not demonstrating. I'm assuming this is true. Okay. Probably if you get some like mathematical physics book, you can find a deduction of this, and probably you can get it very easily online because everything that has somebody's name, you have lots of people showing how to get that. What I did with this, so I'm assuming this is true. This is true for every value of R, okay? So I'm asking, what happens when I have large R, okay? So if I have large R, I can go to those Hankel functions, and I can ask what happens when I have large arguments of those Hankel functions. I'm writing those here, okay? So I'm substituting this property in that equation that I assumed was true, and then I got this one. Okay.
Okay. Yes. Sorry, I lost myself.
Never apologize for those kinds of questions. Please, if you don't see how one line of my slide connects to the next, please let me know. I want this to be clear for everyone. Okay.
Okay, thank you.
All right, so we have this asymptotic behavior. That's the fancy term, but this is just how does a plane wave look very far from the origin, okay? All right, so that was in the case that I had just a plane wave, so my potential was 0. Now, of course, we want to consider cases where my potential is not 0. So for my wave function far from the origin, which includes the plane wave, but also the spherical wave that we got from the scattering that took place, okay? I'm going to write the solution here that, as I'm stressing, is not valid just for the plane wave, but also for this interacting part. In a similar fashion to that equation of the last slide, but I'm going to plug here that radial wave function that was the solution to that differential equation that we were talking about, okay? So this here I was expanding on Hankel, spherical Hankel functions. So I'm writing down this here, okay? So I'm expanding on those two spherical Hankel functions. And since it's a second order differential equation, I have two coefficients here that I have to determine based on my problem here. So this equation here is my expansion for large arguments of this particle that's interacted with the scattering center. And here I'm comparing with the second equation that we got in the last slide, which is the same thing, but just for a plane wave. So for a plane wave, no scattering took place. Okay, so here this one has scattering, and this one doesn't. Okay, so let's compare the two of them, right? So you see that what's important is these coefficients in front of those complex exponentials. By controlling those coefficients, I can see how much scattering took place or not. In other words, I can set these coefficients here to match this one, and then I would have just the free particle solution. If those coefficients are different from the free particle solution, I know some scattering took place, okay? So what's really important about this equation here is those coefficients, right? Actually, what's important is the ratio of those coefficients. By looking at the ratio of those coefficients, I can tell if there was some strong scattering going on or some small scattering going on. So that's the really important part of this expansion, those two coefficients. So they're so important that I'm going to define the ratio of those coefficients as this quantity S here. It's going to be related to the scattering matrix, the S matrix, if you ever heard about it. Of course, it's going to depend on what partial wave I'm considering. So what's the value of L? And I'm going to write these coefficients in this form here, which at first glance, you can ask me, Lucas, that's a very complicated expression. Why are you writing in this manner here? I hope in a few slides I convince you that's an interesting, it's a good choice for writing this ratio of those two coefficients. But if I do that, I can rewrite that expansion for large distances of my wave function, which now has which now depends on the ratio of those coefficients in this manner here, okay? So right now we have everything that we need to discuss this scattering in terms of this new quantity delta that I included here. I know it's a lot of math, but I'm getting to some place that you'll see physics, okay? Just hang on a little bit, okay? So I'm thinking that first equation that I wrote, the equation that I wrote in my very first slide, I'm going to expand the plane wave portion using that identity that we were talking about. And then I can compare with what I wrote in the previous slide here, okay? And then you can see how this term that I introduced here pops up, okay? It's going to be modulating the term with e to the AKR. I'm almost done with the math. What I'm going to do is, maybe I should go back here a little bit. I'm going to try and get from these equations here, those two here, this guy here, okay? Why is this term here important? Because this is going to control, this is going to tell us how strong was the scattering that took place. Because imagine this was 0, okay? So if this was 0, I just have a plane wave and I don't have a spherical wave, meaning no scattering took place. Depending on this term here, I can get more of this spherical wave, okay? So that's what I'm doing here. I'm collecting all the terms in that last slide, and I'm writing those in terms of that phase that I wrote earlier. And you can look at each term of this sum separately. That's what's called the partial wave analysis that I was talking about. And if I write the component for a given angular momentum, I get this expression here. Okay, so this is relating each one of those terms multiplying the spherical wave function, depending on the angular momentum, in a simple manner. It depends only on the momentum, K, and that phase that I introduced earlier, okay? And of course, we can relate that to that S matrix element that we saw previously. A lot of math. Hang on, I'm getting to something, okay? Just bear with me. Now we can discuss something about what happened in terms of that that F and that phase difference that I was talking about. It turns out this phase difference is the difference between the phase of the incident wave function and the scattered wave function, okay? Why is that? As I said before, I'm only considering elastic scattering, okay? So the probability of my wave function is conserved, meaning that if I have some scattering center here, some particle interacts with it, and then it's scattered. If I compute psi square here and here, I can't lose probability. So the amplitude of my wave function is conserved. The only thing that can happen is that I change the phase of my wave function, okay? So this phase here is exactly this phase difference between this incoming wave and the outgoing wave, okay? If I have no potential, I have a free particle, there's no phase difference. The phase of between the income and the outgoing wave is the same. So my scattering amplitude is also 0. Now, if I have some potential that's different than 0, remember this is only acting for distances smaller than the range of my scattering center. There's going to be a different phase between the wave function inside and outside the range of my potential, okay? Why was it important to do all the math that I did up to get to this point and describe my problem as differences in phases, because you can see that scattering is a very hard problem. You saw all the equations that I wrote up to this point. So if I can reduce somehow, I want to trade the problem of calculating a wave function that can be very complicated by trying to describe the exact same physical phenomena, but just in terms of one quantity. And this quantity is going to be the phase difference between those two waves, okay? Of course, I don't want to sound like this is just a number, because this is going to depend on what angular momentum components you're considering, but also the momentum of your particle. So it's really calculating lots of phases that are going to depend on the energy. Okay, but visually it's much easier to understand scattering if we think about this phase. So here I'm just showing this red dashed curve to be, it would be the free particle solution. So it's just a sine or a cosine here. And I have some potential acting here up to a range R, okay? And it's going to be repulsive. So intuitively, what happens if I have some repulsive potential near the origin? It's going to push your wave function away from the origin, okay? And when it pushes, it introduces a phase difference between the two solutions. Of course, outside the range R of the potential, V is 0, and then the two solutions are the same. The only difference is a phase, okay? I can also have the same type of case, but for an attractive potential. So this second figure is up to a range R here. I have something attracting the particle towards the origin, meaning that I'm pulling the wave function towards the origin. Again, outside of the range of the potential, I'm going to have two free particle solutions, but for the one that was pushed towards the origin, I introduced a phase difference between them, okay? So that's much easier, at least for me, to visualize than those complicated asymptotic behaviors. So that's one of the advantages of translating your scattering problem in terms of a phase shift problem. So the question that I have for you right now is, that was a lot of math. Probably you have to go through the calculations yourselves, because me flashing some slides is not going to be enough. But my question is, based on this picture here of, you know, phase differences, can you see how this is a good way to describe scattering? Do you have any questions?
Lucas?
Yes.
Hi, Lucas. I have a naive question. I don't know if I lost something, but what's the physical meaning about the positive and negative potential in the scattering system?
Okay, good question. All right, so we have this problem of a plane wave hitting the scattering center. Okay, so we assumed we made some assumptions on this V of the scattering center. One of them was that let me write it like this. So V is 0 for distances greater than the range of the potential, and it's non-zero for distances smaller than this potential. And we also assume it was spherically symmetric. That's why I'm writing just R and not R vector, okay? Now, we can consider many types of potentials. More towards the end of the course, I'm going to show you some concrete examples. And actually, next lecture, we're going to solve specifically one case, which is the well, the spherically symmetric well, that's going to be just 0 outside the range of potential. and some constant inside the range of the potential. But besides that, I wasn't saying much about the scattering center. I was just saying that it's some potential at the origin. It can be purely attractive, as I'm showing here, right? So it's just a constant here, attractive constant for inside the range of the potential. It can be purely repulsive, as I'm showing here. So it's just a repulsive, so it's a positive constant. It can have some shape. It can be a combination of attraction and repulsion. So as long as it's spherically symmetric, we can deal with the potential in this framework that I'm showing you here. Did I answer the question?
Yes, yes.
Great.
I have a question too.
Okay.
It's like the same question. The attractive or repulsive potential have some connection with the low energy limit that we are considering. I thinking about the nature of the the problem and the potential itself, the microscopic nature of the potential and the barrier that we are considering, the wavelength of the particles of the barrier we are considering, the wave that is inciding on the potential. I don't know. I thinking something like
No,
that.
this is
No?
a great question. No, this is a great question. Okay. So far, I'm talking about scattering. Well, non-relativistic, but besides that, I made no assumptions about the energy of the particle. Okay.
Oh,
So
yeah.
so far we're dealing with scattering, but no assumptions on the energy of the particle.
I see. I think about
Very,
something about the penetration depth of the something. I don't know.
and in just a few slides, we're going to talk about this. We're going to discuss. We're going to focus on the low energy limit, and your question is actually going to be my question when we get to that slide. Okay, so
Okay.
I'm going to flip the table, and then I'm going to ask this question to you. Okay.
Okay,
But
thanks.
that will be very soon. Okay. And okay, so formally, how can we compute this phase shift, this phase difference? If you go to a textbook, it's going to say just take the logarithm derivative. When I was a student, this was very puzzling to me, at least the first time that I heard this term. And
Hear me?
yes.
Oh, sorry to interrupt. Can you go back one slide, please? I have a question.
Yes.
So
Sure.
the behavior you're showing us for the phase shifts being positive or negative, is only for the L equals 0 or for every L, every angular momentum?
So here, so as I said, the phase shift depends on the partial wave and also on the energy of the particle. So it depends on L and also K. So here to do this plot, I chose a particular K, okay? So I fixed the energy of the particle. And also I'm showing for the 0 F, L equals 0, okay? I could do plots that are similar to this one, but for different partial waves, or for this same partial wave, I could vary the energy of the particle. So here I just had to pick one case to show you, but the idea of a phase shift is the same regardless of the energy or partial wave. Okay.
Okay. Thank you.
Good. All right. So why is it called a log derivative? It's because if you compute the derivative of log of a function, what do you get? You get the derivative of the function divided by the function itself, right? So this is very good for lazy people, because if you compute this log derivative, we know that wave functions, they need to be normalized. If I compute this ratio here, I don't have to worry about the normalization of my wave function, because it's going to have some normalization on the top, on the bottom, and they will cancel. Okay. So every time that you hear about log derivatives is because somebody's being lazy. Okay. Since I'm lazy, I'm going to do this. Formally, you're going to say that the normalization of the wave function drops out, and then you don't have to worry about it, right? If we want to work with dimensionless quantities, which is going to be something important towards the end of my course, because we're going to solve some simple problems numerically, and then we want to work with dimensionless quantities. The derivative and the function, they differ by a factor of distance. They have different units related to the distance. So I'm just going to multiply by r here so that we have some number that's dimensionless, okay? And we can look at this log derivative coming. So the potential for example, an attractive potential up to some range r is going to result on some wave function here up to r, and then from distances greater than r, it's going to be just the free particle solution, okay? So we can always look at matching those two types of solutions at this point here, right? So r equals capital R here is our matching point, where we match that the solution outside the range of the potential is just a free particle, and inside the range of the potential, it's going to be the solution to whatever particular potential you chose, okay? So that's the idea. To compute the phase shift, we have to look at this point where we match those two solutions, okay? And that's what I'm doing here. So here I'm coming from the left, okay? Coming from the right, if we write our solution that we got a few slides ago, that depends on the phase shift. If we expand those spherical Hankel functions as complex exponentials, here we have the solution for a free particle outside the range of the potential. And we have to match those two solutions, okay? Little bit of math here. So I'm matching those two solutions. And then I have an analytical expression for the phase shifts, the LF phase shift as a function of the momentum of my particle in terms of that matching that was done. That depends, of course, on the particular potential that we have. The range of the potential, this capital R here, the momentum, of course, and those spherical Bessel functions of the first and second kind, okay? It's an ugly expression, I know, but it's analytical, and in principle, we have everything to compute this, and then we can get the phase shifts analytically, okay? We don't have to plot things and look at what's the phase difference. No, we have this close expression, okay? I'm going to come back to this more towards the end of my course when I discuss explicit examples of computing phase shifts with like explicit potentials, all right? I know it's an ugly expression, but do we have any questions so far? No? Can I continue?
Yes, can continue.
Yes.
Okay. All right. So as I said, so far we only talked about scattering in general. We didn't focus on this low energy limit. All right. So I repeat the question that I started this course with, the question that our colleague asked earlier. What is the low energy limit, right? So we already know that it's going to depend, right? Depends on the problem that I'm considering. But with this formalism that I just introduced, can we say something about what's low energy? So the question is yes. If we didn't think too much, we could say, oh, low energy is when I have energies that are close to zero or Ks that are approaching zero. Okay? And that's low energy. I set E equals 0, K to 0, and that's it. Okay? But we don't have to be so strict. We can also, well, in physics, there's no such thing as 0 or infinity, right? We have things that are very small compared to others or very big, very large compared to others. So this is the case here. We don't really need the energy to be 0. We just need it to be smaller than the other typical scales of our problem. So here I'm going to show one length scale of our problem, which is, as our colleague was asking a few minutes ago, the wavelength of my particle, right? So I have my particle, it has some wavelength, and then it's going to approach my potential. We know that if this wavelength is small enough, so my particle has energy that's high enough, it's going to be able to tell apart this potential that has some characteristic length scale r, right? It's going to feel this. But what happens if this wavelength is very large? It goes through this potential here, but it almost doesn't feel this because this r here is much smaller than this typical variation of this reduced wavelength, right? So my wavelength here, it's proportional to 1 over the momentum of the particle. So if my momentum goes to 0, so if I naively set my momentum going to 0, is as if this particle has an infinite wavelength, okay? So from our discussion here, this wavelength, it can be finite as long as it's much larger than all other scales in my problem, one of them being the potential range, right? So what we really want is this reduced wavelength or the wavelength of my particle being much larger than the range of my potential so that it doesn't even see the potential, okay? So if I express this inequality here in terms of the momentum and the range of my potential, what is the low energy limit here? The low energy limit here is that this product, momentum times range of my particle, has to be really small. I don't remember the name of our colleague that asked the question a while ago. Is this the type of thing you were thinking about?
No.
No. So then you're thinking about my next slide, okay? And my next slide, I'm going to relate this to angular momentum, probably. Let's see if it helps, okay? So if I go back and write that differential equation that we were trying to solve for a partial wave, for a fixed partial wave, so a partial wave L here. It looks like this. So we have the potential, and then the angular momentum part, it's going to give rise to a centrifugal barrier. So I can look at this as being an effective potential. That's the sum of those two terms. And this term here, the centrifugal barrier, probably you already saw this, even in the classical context when we are studying classical mechanics, this appears also. This here, it's repulsive, see the plus sign here, and goes as 1 over r squared. So as I approach the origin, this quickly goes to infinity. So this is preventing my particle from accessing the origin here. Okay, so for every partial wave that's not zero, I'm going to have this barrier, and it's going to be stronger and stronger as we increase L. And it's not going to be present only when we have L equals 0, okay? But we are focusing on these low energy limits, where K times R, it's small, right? So my particle doesn't have energy to overcome this barrier and go towards the small distances where we have the range of our potential acting on the particle. So what happens in the low energy limit is that the particle, for those higher partial waves, cannot enter and access the region where you have the non-zero potential. So for low energy scattering, what's important is the L equals 0 component, because all other partial waves, they're not going to be important because the particle simply doesn't have enough energy to reach this region where the potential is acting, okay? So the conclusion here is when we're looking at low energy scattering, we just have to worry about the L equals 0 case, all right? Another way of seeing this, like a hand waving argument, is my classical angular momentum is R cross P, right? Which is related to our problem, R times K, right? So in the low energy limit, this product here has to be much smaller than 1, meaning that we can only have small angular momentum contributing. In this case, only L equals 0. Albert has a question. Albert, are you typing? Okay, I don't know if, are you trying to use the mic or typing, Albert? Okay, I'm going to continue with the lecture, but I guess Albert's having some problems. And please send your question through the chat, or if you solve the problem with your mic, you can ask the question. You guys are hearing me, right?
Yes.
Yes, we can
Yes.
hear you.
Oh, okay. All right. So any questions?
No.
All right. So using that.
Excuse me, I have one question.
Yes.
From the beginning, we were using the Schrodinger equation, so we knew that we can only focus on low energy limits, right? Because it's a
in the beginning,
equation.
we are using the Schrodinger equation, meaning that we could deal with non-relativistic processes. Okay, so I agree with you that our focus was not relativistic from the beginning, so non-relativistic. But here, I'm restricting even further. I'm saying we could consider non-relativistic process that were, in this context, relatively high energy. But then I'm going to restrict even further to these cases here. So this case is here, where the momentum of my particle times the range of my potential is really small, okay?
Okay.
So there is scattering that's non-relativistic besides what I'm doing here. Here I'm doing something specific with non-relativistic scattering, okay? Okay, so here I'm going to borrow what they use, the spectroscopic notation, right? L equals 0 is S, L equal 1 is P, and so forth. So you're going to hear a lot of people saying S-wave scattering. What's S-wave scattering? It's scattering when you consider just L equals 0, all right? So what we can do is we can go back to those equations we had before and see what they look like when I plug in L equals 0. That's what I'm doing here for that radial wave function. So it's going to look like this in terms of the phase shift. And now I'm just going to consider the L equals 0 phase shift, or as it's called, the S-wave phase shift. Okay. Next, I'm going to solve the Schrödinger equation in this case, which is zero energy. So I'm going to take my momentum going to 0. Is S wave, so I'm going to take L equals 0. I'm going to solve outside the range of my potential, so V equals 0. And then I get this Schrödinger equation here. That's my favorite Schrödinger equation to solve. It's the easiest Schrödinger equation you ever solve, which is just a straight line. The second derivative equals 0, okay? But I'm going to write this straight line in a very particular way here. I could have written something like A times R plus B, something like that. But I'm going to write it like this. You'll see in a minute why I chose to do it like this. And to take that log derivative that I was talking about, which is really just this ratio of the first derivative to the function. It's this simple equation here. And then remember that we always have to match our solutions inside the potential and outside the potential, okay? So this is the solution on one side and the other. I'm matching the two of them. And then if I take this limit of k going to 0, and I'm also setting the distance to 0, I get this thing here. So I get that k times the cotangent of the phase shift in the low energy limits, in the limits that k goes to 0, is just a number. It's just related to this number here, minus 1 over a. And this a here is called the scattering length, something that has units of length, okay? So let's pause and see what we've done. I presented to you scattering in a very general setting as a plane wave interacting with a scattering center, and we had to deal with spherical waves and stuff like that. And I said, that's very complicated. Let's reduce our problem. Then we got to the point where we could describe scattering as phase shifts, right? We are looking at phase shifts that were the difference of phase between an incoming and outgoing wave, a wave inside the range of the potential and outside the range of the potential. But still, we had to look at different angular momentum and the momentum of the particle. Then I said, okay, let's simplify it further. Let's consider this limits where we have very low energies. What happens with those phase shifts when we have very low energies? And at this point, we got something that's just a number. So in these very low energy limits, the phase shifts behave as this. If I know this number, I know the behavior of the phase shift. And in turn, if I know the behavior of the phase shift, I can describe the scattering. So we changed knowing those phases in a momentum range for a single number, and this single number related to the potential. It has all the information at the low energy level that we could ask about our problem. So I think that's very powerful. It's a very interesting that we could do. Reduce our problem to this single number with dimensions of length. And of course, you remember that we had that term that multiplied our spherical wave, right? It was something like f of theta, multiplying that. In this low energy limit, this scattering amplitude is related to this scattering length. So again, just one number in front of this, defining, or better, describing how this spherical wave is going to propagate. In the following, we are going to consider the consequences and the properties of the scattering length. But does everyone see how I got this scattering length and why that's important? Is everyone with me?
Yes, it was very clear. Thank you.
Okay. Aline is asking that she wants to review this lecture later. Okay. This is being recorded, Aline, and I guess they're going to post on the website or let you know by email where the recordings are. In the beginning of my lecture, I said that I already uploaded, or Thiago uploaded the PDF of a paper that's related to this in the website. So if you go there, there's going to be the website. And in the end of my lecture, I'm going to see how much I covered it, and I'm going to send these slides for them to upload to the website as well. Okay, so you have those options. Okay. I'm guessing it's okay. More questions?
I have some way to calculate the scattering length as a function of the capital R.
So this is going to be more clear when we do a practical example. To compute the scattering length, I need a potential. Okay, so if you tell me how does V of R looks like, I can tell you what's the scattering length. So
okay. We don't have the radial potential yet.
Because I'm keeping things general, but tomorrow we'll have like a concrete example, and then we can study that. But
Okay.
if I have some potential that I have the freedom to vary the range, so it can be the spherical L, for example. So I have one potential that's some constant inside the range, and it's 0 outside the range, right? Then your question can be, if I change the range, what happens to the scattering length? Yes, we can compute that. I'm going to show you how to do this. But the answer to your question is yes. If we vary the range of the potential, we're going to vary the scattering length.
Okay.
Also, if we vary the depth of the potential, so this V naught here, we also vary the scattering length. The scattering length is going to be associated with those characteristics. But what's really interesting about the scattering length is, if you tell me a potential, I can tell you the scattering length. But it's not the other way around. Lots of potentials can have the same scattering length. So if you think about it, you say, okay, so if I have one scattering length, which describes the low energy behavior of my system, so I can't know which potential gave rise to that particular scattering length. And the answer is yes, you cannot know. And that's a good thing, because most of the times we don't know the microscopic details of the potential, or they can be quite complicated, can be a very complicated functional form, stuff like that. But since we're dealing with low energy, and this is and the potential has a finite range, the energy is low, so we don't probe the small distances. So we are not probing the details of my potential. The particle doesn't have enough energy to reach, to see the details of the potential. So that's a good thing. This low energy theory doesn't care about the shape of your potential. And for me, this is a plus because you don't have to deal with complicated potentials. You take a very complicated potential and you substitute by a number. Does that make sense?
Yeah, thanks.
Okay.
Lucas,
Yes.
the scattering length could be 0?
Yes, it could be 0, and it's 0 when you have when you don't have a potential. V equals 0 makes your scattering length 0.
Of course, it's not a problem.
No. And you can also ask the other limits. You can ask me if the scattering length can be infinite, and it can, and it's going to be a very interesting situation that I'm going to show you probably tomorrow.
Of course. Spoilers are spoilers.
More questions? Let's see, I think my next slide's about the effective range. No, I have one more slide about the scattering length. Okay, so we saw that the solution to that very simple Schrodinger equation, I don't think it even merits being called the Schrodinger equation, but was just this. It's a straight line. And then I wrote it as this, and I'm going to choose a particular normalization for this straight line, such that I'm going to write it as this. Okay, so why I'm doing this? It's because then I can get a geometrical interpretation for the scattering line. So if I write my reduced rate wave function like this, the scattering length is here. And what happens when r equals a? When r equals a, u is 0, meaning that the scattering length is the intercept. To plot a graph, it's the intercept of the x-axis of your reduced rate wave function. So imagine that I have an attractive potential like this, and my reduced wave function is like this inside here, and then outside here is just that straight line here. Okay. So this point here where the wave function crosses the axis is the scattering length. You can see for this case, A is positive. Okay. If I have an attractive potential, but it's not very strong, meaning it's not going to bind to the particle, it's not going to form a bound state, I have the situation here on the left, which is the potential acts on my particle up to r, and then after that, it's a straight line. But this straight line is never going to cross this r-axis here. But if I do this, I can see where it crosses on the negative axis. So this is a situation when I have negative scattering length. I can also define the scattering length for problems where I have a repulsive potential, which is what I'm doing here. So it's the same thing at r equals capital R. From this point on, it's a straight line. But if I do this, I can get where it crosses the r-axis, and then I have a positive scattering length. So what I'm trying to say here is that by looking at our reduced wave function where it crosses the axis, we can give some geometrical interpretation to the scattering length. If it's a purely attractive potential that's not very strong, I'm going to have negative values. If it's attractive and relatively strong, I can have a bound state, and then it's going to be positive. And if I have a repulsive potential, it's always going to be positive. Okay, any questions?
If the potential is not well, we will have a scattering length that is not constant. Yes.
No, because what happens is the scattering length is always related to the behavior outside of the potential. So imagine that we draw a very complicated potential that's like this, and then does that, and then that it can't do. But it has to stop at capital R. So when you solve this, it can be a very complicated wave function inside here, but as soon as it hits R equals capital R, outside that V is 0, and then it's a straight line. So you can think of every potential that you can imagine, a very complicated potential. You can have a very complicated solution inside the range of this potential. But outside is always going to be this straight line that I showed you, always, because it's always 0 outside the range of the potential. Does that make sense?
Okay, I think I get it.
More questions?
Hi, Luca.
Yes.
I have just one simple question. Like, what is the significance of the A here, of the scattering line that we are using? Like, what does it mean when we are
Yes.
performing an experiment? Like, what is the physical significance?
Okay, so tomorrow I'm going to solve like an explicit example, and then I think it's going to be more clear this. Right now, what I want you to know and get a feeling and understand is that this number contains properties of low energy scattering. And to this point, I just showed you how to get it from this geometrical interpretation. But I'm going to use this number tomorrow to get things like bound state energies and stuff like that. So far, I didn't show you much what you can do. But of course, if you know A, you can always get the low energy phase shifts. And then if you have the phase shifts, you can say something about the experimental situation, if the wave function is being pulled or pushed. Okay.
Okay.
Did I answer at least partially?
Yeah, partially, yes.
Okay, good. I hope tomorrow this will be much clearer.
Thank you.
More questions?
I have a question. When we are talking about an experiment, all the situation we are thinking in ideal terms, right?
Yes.
When we look at a physical system, and let's suppose that this physical system, the plane, the wavelength, oh my God, sorry, the wave functions, they are such that it's described as this U0R, this this line. When we are around this point, the R capital equals R small r, we will see modulations, right? It's not a direct, there is no mathematical terms, is discontinuation in the function. When we are at the point R equals small r, we are going to see some weird behaviors. That's what I'm trying to say, actually. We are not going to see directly, oh, we have a weird behavior inside the range of potential, and just at the point R equals R, we are going to see the straight line. This would be a discontinuation, right? We are going to see some weird things on the point in the physical system.
So what I did to derive this, I assumed that both the wave function and its derivative at capital R are continuous. So you won't have any problems regarding, I mean, you're safe. The wave function and its first derivative are continuous here and in other points. So that's not a problem. Now, you asked something about the wave function inside the range of the potential. So to see things that are in short distances close to the origin, you need high energy, right? So, and if you need high energy to see things that are near the origin, you are not in the low energy limits. The low energy limit is something that doesn't care about the details of what's happening near the origin, okay? So our approach here is going to be to focus on large distances, at least larger than the range of the potential, because our theory doesn't care about the microscopic details of the potential. So that's the philosophical approach to this low energy scattering. So we are not going to worry a lot about the details inside the range of the potential. Okay?
Okay. Thank you.
More questions? So if not, I think this is a good point to stop. And then tomorrow we can talk about another quantity that's important, that's the effective range. But for today, the scattering length, I think it's enough.
Okay, Lucas. So thank you very much. Please send these slides, at least up to this part.
Yes.
Thiago, and then this will be posted.
Aline, você abriu o microfone e fechou rápido? Eu não... sorry, Aline, I couldn't hear what you said.
Não, eu abri sem querer, foi mal. Não consigo falar agora, tá uma barulhinho.